The Starship Deception. Why the real Mars mission is a ghost fleet. An analysis of its own technical architecture reveals a staggering fact. A single Mars-bound Starship reaches orbit as an empty shell, requiring over 1,000 metric tons of cryogenic propellant, to be delivered by a relentless convoy of tanker flights, just to begin its journey. This critical dependency shifts the mission's primary engineering risk, from the celebrated launch vehicle, to an entirely unproven, high-frequency industrial operation in the void, one governed by the unyielding laws of thermodynamics and fluid dynamics. Consequently, to grasp the true viability of the Mars endeavor, one must dissect this ghost fleet's foundational challenges: the tyranny of the rocket equation, the thermodynamic race against boil-off, and the unsolved impasse of transferring liquids in zero gravity. The entire architecture of interplanetary travel is held captive by a single, century-old piece of mathematics, known as the Tsiolkovsky Rocket Equation. A formula that acts less like a guide and more like a warden for spaceflight engineers. This fundamental law dictates that a vehicle's potential change in velocity, its delta V, is governed not by the power of its engines, but by the ratio of its initial wet mass to its final dry mass, a concept brutally simplified as mass fraction. The equation is unforgivingly logarithmic, meaning that each incremental gain in final velocity requires an exponentially larger quantity of propellant, creating a physical paradigm where the fuel required to carry more fuel quickly becomes the mission's dominant mass. It is this inescapable tyranny of physics, detailed in foundational astronautical engineering texts, that frames the operational reality of Starship. To achieve the approximately 9.4 kilometers per second of delta V, needed to overcome Earth's gravity and atmospheric drag to reach low Earth orbit, Starship must ignite with a gross mass exceeding 1,300 metric tons, of which around 200 tons are cryogenic methane and oxygen. Its dry mass, the actual structure and payload, is a mere fraction of that total. As a consequence, upon arriving in Leo, the vehicle has effectively consumed its own potential, becoming an inert steel shell, with its propellant tanks almost entirely depleted. The vast internal volume designed to carry the propellants for the Mars transit, is now a void. Its purpose served just to lift itself and a modest payload, a few hundred kilometers above the Earth. This reality, implicit in SpaceX's own documentation on its orbital refueling strategy, confirms that a lone Starship is not an interplanetary cruiser, but a terrestrial launch vehicle that pays an immense gravity tax, leaving it with virtually zero remaining delta V, for the subsequent multi-month voyage to another planet. The spectacle of the launch, therefore, masks the brutal truth that the real mission has not even begun. It has merely been staged, awaiting a logistical chain of unprecedented scale. The Tsiolkovsky Rocket Equation dictates that nearly 90% of Starship's launch mass must be propellant, rendering it an empty vessel in orbit, incapable of reaching Mars without a massive subsequent refueling. Once a Starship has paid its debt to gravity and settled into low Earth orbit, it immediately enters a second, more insidious conflict: a thermodynamic war against the vacuum of space itself. The high-performance methane and oxygen propellants it carries, are not stable liquids like gasoline, but cryogenics, substances held in a liquid state just a few degrees above absolute zero, at approximately -183 degrees Celsius for oxygen and -161 degrees Celsius for methane. These propellants exist on a knife edge of physics, constantly seeking to absorb energy and revert to their natural gaseous state, in a process known as boil-off. In the Leo environment, this thermal assault is relentless and multifaceted, coming from the intense, unfiltered solar radiation on the sun-facing side of the vehicle, the reflected sunlight from Earth's surface and atmosphere, known as albedo, and the infrared heat emitted by the planet below. This creates a punishingly complex thermal environment, where one side of the stainless steel hull can be baking at over 120 degrees Celsius, while the other, facing deep space, plunges to below -150 degrees Celsius. Extensive research, including foundational work outlined in the NASA Cryogenic Propellant Storage and Transfer Technology reports, has explored strategies for deep space thermal management. To mitigate this unavoidable heat ingress. Passive solutions, such as high-performance multi-layer insulation, and even advanced concepts like vapor-cooled shields, can slow the process. But they cannot stop it entirely. Active cooling systems, or cryocoolers, offer another path by functioning as refrigerators. But they introduce their own set of profound challenges, including the need for significant electrical power, the introduction of vibrations, and the critical problem of rejecting waste heat via radiators. The core issue, as these studies consistently highlight, is one of unprecedented scale and duration. While boil-off has been managed for upper stages on missions lasting hours or days, the Starship architecture requires storing and aggregating over 1,000 metric tons of cryogenics in orbit, for potentially weeks. No technology has ever been proven to operate at this scale, and for this duration, with the near-zero boil-off rates required. This thermodynamic reality transforms the orbital depot of the tanker fleet from a simple refueling station into a collection of thermodynamically leaking assets. Where every hour of operational delay on the ground at Boca Chica translates directly into an irrecoverable loss of propellant in space, shrinking the potential delta-V available for the Mars injection burn. The fight is no longer against gravity, but against entropy. The constant, unavoidable boil-off of cryogenic propellants ensures that any fuel cached in orbit is a diminishing resource, making the entire refueling campaign a race against the second law of thermodynamics, should the physical constraints of mass fraction and the thermodynamic siege of boil-off be overcome. The architecture for a Mars mission confronts a third, deeply counterintuitive physical barrier: the seemingly simple act of moving liquid from one container to another. On Earth, this process is governed by gravity, a reliable and constant force that separates liquid from gas and pulls fluids downward in the persistent freefall of low Earth orbit. Gravity's organizing influence is functionally absent in this microgravity environment. The physics of Zerog fluid dynamics asserts a new and problematic regime, where weaker intermolecular forces, particularly surface tension and capillary action, become dominant. A vast pool of liquid propellant no longer behaves predictably. Instead, it can break into free-floating globules, climb the tank walls, and form a complex, unstable interface between liquid and vapor. Making it impossible to guarantee a pure liquid feed into a transfer pump. The challenge, studied extensively in programs, informing documents like the NASA Cryogenic Propellant Storage and Transfer Technology reports, is that any attempt to pump this unsettled mixture, risks disaster. Ingesting gaseous propellant into a high-speed turbopump can induce cavitation, a destructive process where vapor bubbles collapse with enough force to erode or shatter impeller blades, leading to immediate pump failure. To counteract this, the proposed solution for the Starship and its tanker fleet is a maneuver of controlled force, a brief thruster burn to create a slight, artificial acceleration. This ullage thrust is designed to push the docked vehicles forward, causing the liquid propellant to settle at the aft end of the tank, where the pump inlets are located. However, this solution introduces its own immense complexities, as managing the slosh dynamics of 100+ tons of liquid methane moving within a tank requires careful dampening to avoid destabilizing the entire docked vehicle stack. Furthermore, the ullage burn itself consumes propellant, adding yet another inefficiency to the delicate delta-V budget. The entire procedure, docking two massive vehicles at orbital velocity, establishing a secure fluid connection, performing a precise ullage maneuver, and then transferring hundreds of tons of supercooled liquid, without inducing cavitation or thermal shock, has never been performed at this industrial scale, in microgravity. The absence of a simple down direction turns the fundamental act of pouring fuel into one of the most significant and unproven technological hurdles of the entire Mars endeavor. The convergence of these individual physical hurdles, the debt imposed by mass fraction, the ceaseless attrition from thermodynamics, and the dynamic impasse of zero-G fluid dynamics, creates a final, systemic challenge of staggering logistical complexity. The architecture for sending a single Starship to Mars is fundamentally dependent on a separate, supporting constellation of vehicles, the tanker fleet, which has no purpose other than to serve as a high-speed, orbital supply chain, according to mission profiles based on the vehicle's own specifications. A fully loaded Mars-bound ship requires somewhere between 6 and 10 consecutive tanker launches, each delivering its payload of methane and oxygen, to the waiting vessel in low Earth orbit. This transforms the problem of interplanetary travel from one of building a capable vehicle into one of flawlessly executing an industrial-scale operation, with a tempo and reliability that have no precedent in the history of spaceflight. The operational cadence required from the launch infrastructure at Boca Chica must resemble a relentless conveyor belt, not a series of distinct, grandly spaced missions. The core vulnerability of this entire strategy lies in its sensitivity to time. The accumulated propellant in orbit is a perishable good, its quantity constantly diminishing due to boil-off. Consequently, the system is critically exposed to cascading failures, where a single delay on the ground, a technical scrub, an unfavorable weather front, or a range availability issue, ripples through the entire orbital assembly process. A delay of several days for one tanker launch could allow so much of the previously delivered propellant to evaporate that the mission's required delta-V for the Mars injection burn can no longer be met, potentially forcing a scrub of the entire multi-billion-dollar endeavor. The true measure of the system's success, therefore, is not the peak performance of the Mars-bound Starship, but the mundane, repetitive, and flawless execution of its invisible support fleet. This reframes the entire venture, away from the heroic image of a single vessel embarking on a great voyage, and towards the brutal reality of a high-tempo industrial operation, where the failure of one link in the supply chain invalidates the work of all the others. The success of a human mission to Mars is therefore contingent, not on the power of a single rocket, but on the unproven, high-frequency, and unforgiving reliability of its orbital logistics network. Ultimately, the journey to Mars is defined not by the spectacle of a single launch, but by the relentless, unproven perfection demanded of its invisible support fleet. This ghost fleet, born from the non-negotiable constraints of physics, reveals that the true mission is not a voyage, but a brutal industrial operation staged in the void, where the primary engineering risks lie hidden in the quiet transfer of cryogenics between orbiting tankers. The central challenge, therefore, shifts from building a great ship to mastering an entirely new and profoundly fragile space-based supply chain. If you value this level of in-depth technical analysis, support Dissect Official by subscribing and sharing this investigation, considering the immense hurdles of thermodynamics, zero-G fluid transfer, and logistical timing. Where do you believe the single greatest point of unmitigated risk lies? Within the orbital refueling architecture. Thank you for joining this deep dive. We'll see you in the next analysis, where we'll expose the silent, high-stakes material science war being fought to prevent quantum tunneling from collapsing the future of computer chipsets.